In class, we'll complete the vapor pressure and boiling point worksheets that we did based on yesterday's notes, take new notes, and we'll work on homework about solutions. So a solution is a homogeneous mixture. The components are not chemically combined and they retain their original properties. Example would be that sugar water still tastes sweet when you drink it. It's even throughout, it's a homogeneous mixture. Solutions. A solution is made of a solute and a solvent. A solute is the substance that's dissolved. The solvent is going to be the most abundant component of the solution, and it's the thing that's doing the dissolving. When you're making lemonade, your lemonade mix is your solute, and the water you're mixing it into is the solvent. In class, we're going to be looking at a fat simulation showing molarity. Water is called the universal solvent because it has the ability to dissolve so many substances. Without water's ability to dissolve things, life on our planet wouldn't exist as we know it. Solutions. Remember that an aqueous is a solution where water is the solvent. Example. When we dissolve salt into water, it dissolves into sodium ions and chloride ions. We would have a salt solution. We're also in class going to be looking at a simulation that shows how salts are soluble, how they dissolve in water. Solubility is the maximum amount of solute dissolved into a particular solvent at a specific temperature. So the amount of solute you can have in a solution depends on temperature. You can have 3 different types of solutions. Saturated, which means that you can't get any more of the solute to be dissolved. Unsaturated, which means that you can add more solute. You can add more and it will dissolve. Supersaturated. This is more solute is dissolved than is theoretically possible. In class, we're showing an example with hand warmers where we can turn a substance from a supersaturated solution to a saturated solution and then back again. To make a supersaturated solution, you have to add first more solute than solubility will allow. But then take that and bring it up to a warmer temperature. So you're going to heat the solution up. After you've heated the solution up, everything will have dissolved, and then you slowly cool it down. This is a temporary and unstable state for a solution. When it does go back and you start to get a saturated solution, which means that these particles are starting to turn into a solid, energy will be given off, and so this will be an exothermic reaction, and this is why hand warmers work. Factors that affect solubility. Temperature. Most solid substances have higher solubility as the temperature increases. All gas solutes will have a lower solubility as temperature increases. Remember, the gases are going to have more speed to the molecules, and so they're going to leave the solution faster. Pressure. Pressure only affects gas solutes. The reason why soda cans are under pressure is because we can get more of that carbonation in there. Once we remove the pressure by opening the top, the carbonated gases leave the solution and our pop goes flat. All gas solutes have higher solubility as pressure increases. We can force more of those gas particles in. Solubility curves. For solid substances, you can see that for most substances, as we increase the temperature, we can get more of the substance to dissolve in water. But not all substances behave this way. You can see that cesium sulfate actually has a negative curve. So the warmer it gets, the less of it dissolves. If we're looking at gases, as you can see, for the most part, the higher the temperature, the lower the solubility is. It's very possible that you'll see one of these types of questions on the EOC. The question may sound something like, at 50 degrees Celsius, how much potassium chloride will dissolve in 100 grams of water? All you have to do is follow this 50 degrees Celsius over, and then measure, and I would say it's about 42 or 43 grams of potassium chloride will dissolve at 50 degrees. Rate of dissolving. How fast a solute dissolves in a solvent shouldn't be confused with how much will dissolve. Some things will dissolve at a fast rate, but not very much of them will dissolve in the solvent. Rates can be increased by, first, increasing the temperature. If we increase the temperature, there's going to be more kinetic energy available to meet activation energy, which is basically the energy available for dissolving. We could also stir the substance, increasing the interaction between the solute and the solvent. We're going to move things around faster. And lastly, we can powder. When you powder something, let's see if I can get this to go away. When you powder something, you're going to increase the surface area, which will increase the interaction between the solute and the solvent. We can think of this, if we put a lump of sugar into coffee, it'll take a while for it to dissolve. If we put granules of sugar into coffee, we just stir it a little bit and it'll dissolve almost immediately. But if we took powdered sugar and put that into our coffee, we wouldn't even need to stir it. It would dissolve very, very, very fast. Liquid to liquid solutions. Well, if two liquids will mix and mix uniformly, we would say that they're miscible. An example would be milk and water. They will blend together and they'll mix completely. Immiscible is when you have two liquids which will not mix, and they will form layers. An example of this would be oil and water, like you'd have in salad dressing. The thing to remember is that, as a general rule, like will dissolve like. If you have a nonpolar plus a nonpolar, they will be miscible, and so they will mix uniformly. If you have polar and polar substances, they are also miscible, so they're going to mix completely. If you have nonpolar and polar, those are unlike, and they will be immiscible, which means that they're going to form layers and won't mix completely. We're going to watch a video in class, and that'll be the end of today's notes.